Okay, today, let's get you all prepped for your first actual lab that we're going to do next week. So, next week, I'm going to give you this little solar collector. You're going to have to wire it up to a protoboard with a 10K resistor. You're going to take it outside, and you're going to answer the question, how long does it take to heat a 40-gallon tank of hot water from 50-degree ground temperature to 140? Now, you need to get some background in. Just for my own edification, how many of you guys have ever touched an Arduino or programmed it? Alright, so I'm looking at maybe a third. Okay, that's cool. This is not a programming class, guys. I'm going to make this really, really easy. But it's still something that you should know. Okay? Basically, what I want you to get out of this is, I want you to know what a microcontroller can do for you. That's part of what this lab is about. Okay? I'm not trying to make you an expert, but I want you to know what you can ask a software guy for or an electrical guy for. Hopefully you went over to here and you've got the Arduino IDE or the programming environment all set up on your computer. It's free. When you start it up, it should look like this. Okay, I can hammer at you a whole lot, now let's just jump right into it. Okay, here is the actual Arduino programming environment. Okay. First thing you see up there, you see a subroutine called void setup. Okay, that is a setup routine that is going to run just one time. So if you've got a bunch of startup housekeeping, like establishing communications and stuff like that, you only got to do it once, or maybe you're writing out a file header so that you label your columns as, you know, elapsed time and temperature of sensor 1. You can put all that stuff up there in void setup. The next section, void loop. Okay, that is a looping routine that is just going to keep going and going and going and going forever and ever until you take the power away. In this IDE, there are lots of examples that are built in. So if you don't know how to do something or you want to see an example, just click on File and come down to Examples. And even under Basics, okay, there's a little program called Blink. If you want to just flash the onboard LED, you want to see how that's done, here's a program that just blinks the LED. So we have a comment section, giving credit to the writers, void setup. First thing we do is we set the pin mode, we set the pin to an output. On the Arduino, digital pins can be either inputs or outputs. You should tell the chip whether it's going to be in or out. If it's output, you can write to it, you can make it high and low, 0 and 5 volts. If it's input, you can read the pin and you can ask the chip, okay, do I see any voltage on that pin? If it's a digital input, pretty much anything above 4.5 volts is going to be considered high. Anything 4.5 to like 2.5 is indeterminate. You'll get weird readings. I strongly advise just make it either 5 or 0. A lot of times you'll just do that with a switch and a resistor. Okay, we come down to void loop. So we say digital write. This would be better stated as the actual pin. So this is defined as pin 13. In fact, let me just modify this. that is equally acceptable. So all I'm saying is, I'm going to write to a digital pin, on pin 13, make it high. Turn it on, put 5 volts in. The next line, delay 1000, delay 1000 milliseconds. That number is always an integer, it's always in milliseconds. The next one, digital write, pin 13, low. Turn the pin off. Okay, undo part. And then delay 1000, wait another 1 second, and keep doing it. Just go round and round the void loop. To get this from something that we can read as humans into the Arduino, we will first plug our Arduino into our mighty fine USB port. That powers it up. You don't need any external power. You don't need a battery, anything like that. USB protocol provides for power. You have to come up here to tools. You got to tell it where the Arduino board is and which board you're programming. So there's megas, there's Unos, there's stuff that's Wi-Fi enabled, there's nanos. You got to tell it which board. So if you're doing this for the first time, it probably won't have anything in there. Come down to AVR boards. There's a list of all the Arduino boards. Everything we're going to do in this class, I'm going to give you 2560s, the megas. They have a little bit faster processor, they have a little bit more RAM, and they have some extra analog ports that are kind of nice. So everything we do is going to be this one, Arduino Mega. Next, we'll come down to the port. So when I plug that in, it says, aha, I see a Mega on COM6. Great. Make sure that's clicked. And now, up here, this is verified. So if you just want to check your code, make sure it compiles properly into machine language, you can hit that. Okay, if I had any errors, I would see a bunch of errors in red. I'd have to go back and fix them. This says my code is good to go. So if I click on upload, it recompiles the sketch. And now that Blink program is in the microcontroller. So if I wanted to, I could take my little microcontroller, which is now deactivated, there's no onboard battery, and I could plug in, a battery. As soon as I plug it in, that program is going to start running, and the onboard LED is going to blink again. Okay, so it's not volatile memory. You're writing to flash, so it stays in there until you overwrite it. Okay, that's a super simple first example. But because this is not a programming class, I've made a template for you. So we have an MEE365 coding template. And let's go through it. So /star, that means everything after that's going to be a comment until you see /star. So this is all a comment. I want you to start off with some description of what the program does. What is this? I can't tell you guys how many times out in industry I worked on a project, set it aside for 6 months, and then they said, hey Steve, where's that thing you did a year and a half ago, or 6 months ago? And then you got to come back and resurrect it and go, oh God, what did you do? Okay? So make sure that your stuff is well commented, well documented. I am going to be looking for that. Okay, so this code allows your Arduino to read a DigiKey, blah, 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 thermistor, and output values to the serial monitor. This next line, okay, this double slash, that's also a comment. So nothing is being executed here. But I put it in there. If you have any includes, any header files, you can expand the Arduino's ability by adding modules of code, and that's where you would put it. So for example, when you guys get the capstone, let's say you wanted to take this little Arduino and make it act like an RC transmitter so that you could take your electric motor, throttle it up, throttle it back. Maybe you're going to make an autonomous drone, you want to move the elevators left and right, driving servos. There's pre-made code already out there that you can just include, and then you can declare a servo object and tell it what angle you want the servo to go to. Really nice. So you could have this include servo H, and then you have all that functionality ready to go. That's what that's doing. Next thing, I have another comment. I say declare variables. So anything you're going to use. INT means integer. 1, 2, 3, 4, 5, no decimal places. Because this is a relatively simple processor, okay, you cannot just have any value you want. So it'll store anything from minus 32,768 to positive 32,760 should be 8. Okay. And that's simply because you've got 16 bits up, 16 bits down, but you got to have 1 bit for the minus sign. So again, another integer called sensor value. You can predefine them the way I've done there. That's fine. Sometimes you need to store a really big integer. So if you're trying to time something in microseconds, you might need more than 32,000 stored in a variable. That's where an unsigned long comes in. It's just an integer, okay, but it can be much, much larger. So you get a 32-bit number that you can store in that. Okay. These are used in timing stuff, which we're going to do when we start looking at thrust-specific propulsion. I'm going to ask you guys to time the rotational speed of the blades and when they break the laser. So you're going to need that kind of big number. Okay, floats. Decimal numbers. So your floats could be something like A equals 0.003, blah, blah, blah. That's how you store decimal numbers. And really, that's all we're going to need for this class. So if you know ints, just integers, unsigned longs, which is just big integer, and float, which is decimal numbers, you're good. Okay, now we come down to void setup. Again, this is the thing you're going to do one time. It's your initial housekeeping to get everything ready to go for the program. First thing I said, serial dock again, 9600. What that command does is it establishes two-way communication with your computer so that it can read information, send it back to the PC. Serial print ln, blah, 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 a whole bunch of stuff. Okay, so I mentioned maybe you want to write out the file headers for what's coming. That's exactly what that line is doing. Serial print is how I say, send this stuff back to the computer. If I put it in quotes, it becomes a literal, and it sends exactly what's in the quotes. Okay, now we start actually doing the program. So avoid loop, this is the thing that's going to happen over and over and over again. So the first thing we do, we say time equals millis. Okay, millis is a command, and it says return the number of milliseconds the program has been in operation. Okay, that in itself is not super useful, but what you're going to use it for is change in duration. So maybe you need to time a propeller. You know, if you take one time when the propeller passes, and then you get the next time, subtract 2. Now you got the duration for when the propeller came around, you get speed. That's the way we're going to use this. Okay, so I'm going to then serial print the time. So I'm going to send that millis integer stored in time back to the computer. The next thing I'm going to do is print a comma, the literal, a comma. It's in quotes, it just sends a comma. Okay, we're going to see how that comes into play when we start sending information back to Data Streamer. So the commas are going to say whatever value. Okay, now jump over one column in Excel. That's what that's doing for you. Next thing we're going to do is we're going to read the analog or the measuring pin A0. Your analog pins can read any kind of variable voltage within the range of 0 to 5 volts. Okay? So if you read pin A0 and it brings back a number 0, there's no voltage. If it sends back the value 1023, there's 5 volts. And it scales linearly. So if it sends back 512, there's 2.5 volts. It's just a linear thing. But what I've done is I've created a for loop right here. So I do an analog read and I say, what's the voltage on pin A0? It returns an integer that's proportional to the voltage. And then I take and I sum up all those sensor values with a delay of 2 milliseconds. Why the heck did I do that? Pretty simple, guys. That is the quickest and easiest way to get rid of electrical noise. So what I'm doing is I'm taking an average of 100 readings to get rid of noise. It does cause your data to shift back a little bit in time. Okay? But for some things like watching the temperature of this thing rise for a half hour, if my data shifted back 5 milliseconds or half a second, I don't really care. If I was timing something really fast, like a supersonic flow, yeah, then I'd care. But for this, not so much. So that's going to give me a nice stable reading that's not jumping around a lot. Okay, so then I average my sensor value. I just say, take that sum, divide by the number of readings. So I started off with my 4. I started with initial I value equal to 1. I'm going to keep looping in this 4 while I is less than or equal to 100. And every time through, I increment I by 1. I don't do anything with I, but I just use it for a count. That's all it's in. Okay, so I get my average. I do a serial print. I print it to the screen. And then I print a literal comma so that when I send this stuff to Excel, it jumps into the next column. Next thing I'm going to do, so I've got this bits value coming out of A0 in the range of 0 to 1023. Okay, so not really useful. So the first thing I'm going to do is convert it to voltage. So I've got a variable called A0 voltage is equal to my average sensor value times 5 divided by 1023. Simple scaling stuff. And then I output that voltage and then output a copy. Next thing I do, great, I've got the voltage. But what I really want is the resistance of this little temperature sensor. Okay. That is going to be useful information. So I take the voltage divider equation, I do a little algebra, and the resistance of this thermistor, or temperature sensor, is equal to that equation, 50,000 divided by A0 voltage minus 10K. We're going to print that to the screen, and then I'm going to print the comma. Again, so I jump over another column. And then this really complicated formula, which I just gave you, which we're going to talk about in 375, but not here. This actually converts the resistance of the thermistor to a temperature in Kelvin. So now I've got my sensor temperature, which is really what I want. I print a comma. I'm going to convert from Kelvin to Celsius, and then to Fahrenheit. Delay 1 second. And I do that again and again and again. That's going to be your 365 template. So let's see what it does. So I'm going to shoot this into the memory. So it's doing exactly what you would expect. So here's the elapsed time. The reading was taken in milliseconds. Here's the port voltage. Port bits. Port voltage. The resistor, the Kelvin temperature, the Celsius temperature, and the Fahrenheit temperature. And that's great. You can sit there and watch the data scroll by all day long. That's not going to help you write a lab report, however. And that is where Data Streamer comes in. So instead of writing to the screen like this, we're going to write that into Excel. So as long as we've got everything formatted properly, everything in nice columns, and then going on to new rows, this is going to port right over to Excel. One thing I forgot. That line right there. See these serial prints? Okay, they just keep tacking it right onto the same line. If you want a new line, you say serial print LN. And that does carriage return, brings you back to the start of the next line, then you can get the next one. So you should always end with the serial print LN when you start the new line. You could also do serial print /n. That works too. It's up to you. But I generally do this. Here's where I got in trouble when I started this. So the USB port cannot be shared by application. So I can't have Arduino up and have Excel up at the same time. So I'm going to have to turn off the Arduino. And now I'm going to come over here to Excel. I'm going to open a blank workbook. guys did your homework, and you should see something called Data Streamer right up there at the top. When you click on the Data Streamer tab, you should get something that looks like this. Okay, first thing we're going to do is we're going to connect our device. Ah, look at that. Arduino Mega, COM6. Let's listen to that. Okay, so now it knows what to listen to. I'm going to click Start Data. Okay, and here's all the data being put in nice, neat columns in Excel. Pretty snazzy. You can have up to 500 lines of data, which for this course is going to be totally adequate. I'm going to give you a sampling rate that's going to work with your labs, so you won't need more than 500 lines. If you wanted to write your headers again, there's a little red button on the Arduino right there. Just press that. That's your reset button. So I reset it. Okay, anyway. So you might have to move those over. But there's all your headers, and now my time started back close to 0. Again, we're going to be looking at delta changes in time, so that's not super important. Okay, so we've got the data that's just scrolling through right now. The important thing, and I know this is going to mess with somebody because it messed with me, you got to hit record. Now I'm actually recording the data. It's not just flashing by. I'll hit the reset. And now I'm starting to take my 500 lines of data that I can actually use. So this is actually going to be your, I think it's lab 2, where we do psychrometrics and humidity stuff and mixed gases. So let me just put my hand on this. It has the exact same temperature sensor. We're going to use the same temperature sensor throughout the entire course, so that fancy equation will be applicable everywhere. And you can see from the last column, yes, I am in fact alive, the temperature is going up. Good enough. And temperature's coming down now that I've got my hand off it. Okay, here is the important thing. Hit stop recording. Okay, as that data is being streamed into Excel, it is not being written to disk. It is being stored in memory. Until you hit stop recording, you will not have a data file. Ask me how I know. I'm going to just call this test. And it's creating a file for the .csv extension using comma separated values. That's why we wrote all those commas back in the Arduino code. And I'm going to hit save. So let's say file, open it, I browse for it, I'll go to my desktop. I just had to change the file type down here. It wasn't coming up automatically, so I changed it to text files. That brought up CSV. The CSVs are nothing more than a plain old text file. You could modify them in Notepad if you had to. Okay, so it's going to do an import. It says delimited. Is there some character in the middle of the columns that's going to tell me when to go over to the next column? Yes, because we put the commas in. Okay, so I'm going to choose my delimiter as commas. I'll say next. Column data format general, yeah, that's fine. And finish. And here is the data that was coming out of the Arduino. So you may have to clean it up. I'll get rid of that. And stretch out our columns a little bit. And now you can do whatever you want to, do math in there. If you want to bring this over to MATLAB or something you're more comfortable with, I don't care. Use whatever number cruncher works best for you. So I'll insert a chart. And select some data. There's the temperature profile of that block. So it's pretty steady. Put my hand on it, took my hand off, the temperature dropped off, and there's the time. I would probably convert those times to seconds. So you could just do something like this. Still the same duration. Okay, so that is how you're going to get data from the Arduino into the computer, into Excel, ready for come to lunch. Okay, let's talk about what you're actually going to do. You're going to do something very, very, very similar. In fact, that 365 template, you could just shoot right in. Okay? I would ding you for not having it properly commented, but it would function. Okay, you're going to do a nice formal report for me. You're going to use that report template that I gave you last time I hammered at you. And it's all going to be about how long does it take to heat a 40-gallon hot water heater, a 4x8 foot flat plate solar collector pointed directly at the sun. So you know the mass of this thing, you're going to data log the temperature, you know the area of it, do a whole bunch of cool stuff. At least I thought it was cool. Okay, so this collector is 6 inches by 6 inches. The aluminum is 203 grams. It's 6061 aluminum alloy. And it is blackened with rust-oleum, because I like rust-oleum. It's got a 10K thermistor inside, not really relevant. Before you show up, I would like you to create an Excel spreadsheet where you say, I have a variable cell value, which is going to be the insulation. So maybe you want to assume 1,000 watts per meter squared. So if I've got 1,000 watts per meter squared striking a 6x6 surface, you know the energy coming in. You know the mass. You should be able to get the rate of temperature increase. When you do the lab, you're then going to superimpose your actual results versus your theoretical. Okay. And then also pre-lab, create an Arduino program that sends a plate temperature and elapsed time back to Excel approximately every 1 minute. Your wiring is going to be just like this. So you're setting up a simple voltage divider. We're going to come off the 5-volt pin. We're going to power the 5-volt top rail. That's going to go into the thermistor, which is inside here, down to a 10K, down to the bottom negative rail, and back to ground. I mean, honestly, guys, this is one, I just want you to get your hands on a protoboard so when you're not in capstone, you don't say, well, how's this thing connected? You're going to get a chance to practice. Okay, so for the lab procedure, create a folder on your computer for the lab results. I would create a folder called MEE365. They call it Insulation Lab. Do a function check before you go outside. Make sure you're getting good data back. Make sure that it reads something like room temperature, and you're not getting, some data that says it's 500 degrees in the room. That might be wrong. Before you go outside, cover the collector with a piece of paper so that you can sit there, you get all set up, get everything good to go, and then go and pull the paper away. Do your best to keep it perpendicular to the sun. Begin receiving and recording data. And recording. Somebody's going to get burned by it. I got burned twice. Watch your temperatures go up. Do not go above 102 C. At 102 C or 33 minutes, press stop recording. Remember, data is only written when you hit stop recording. I will be out there with you. I will give you the actual solar insolation, the strength of the sunlight. I have a device called a pyrometer that will measure it so you can get an actual versus a theoretical for your collector. And then put your results, theoretical versus predictive. Excuse me, theoretical versus actual. Your lab questions. Show all your work neatly with equations written out, just like I did in the sample write-up. At 4 minutes, what is the actual energy increase in the block in joules from the starting temperature? What is the average power being absorbed by the aluminum between 240 and 420 seconds? What's the average heat flux? Power absorbed divided by the collector area at 240 and 420 seconds, watts per meter squared. What should the temperature be for the block at 240 seconds if all the sunlight were completely absorbed, remained constant, and there were no real-world heat losses? What's the percentage of the sun's energy that was captured at 240 seconds Basically, what's the efficiency? Okay? And then you come in and you can finally answer the big question at the end. How long is it going to take to heat that tank of hot water? Based on the capture temperature. Just go ahead and assume that, obviously there's no water flowing through this thing, but assume it has a perfect heat transfer to any water that could flow through it. All right? Okay, that was a lot of stuff, guys. Any questions? Seem relatively straightforward. Okay. The weather is looking good for next week, so we should be able to get outside without getting rained on before the hurricane comes up the East Coast. Should. If you decide that you want to just do it early, I have no problem with you taking this thing out of the closet and doing it early. If there's a nice day where you're bored and you just want to go work on your cans. That's completely fine. You do not need to bring your Arduino to class. I will have Arduinos and all the stuff there waiting for you. So just come to the dry lab, Berlin, 234. You can do your function checks.